with that, I just want to add, Warren also works with LIGO. We're actually a large collaboration of a bunch of different institutions. Warren is actually a physicist. I'm not, I just play one on TV, but that tells you which one of us knows what we're actually talking about. So I'm going to talk about policy and usability issues with passwords, and Warren's going to get into the fun, hard science stuff. So, passwords. They're the worst authentication system in the world, except for all the other ones, right? They're here to stay. We're stuck with passwords for all kinds of reasons. We don't really have a viable general purpose replacement for them, certainly not for some time. And if somebody comes up and says, well, what about PAI? I've got this SM57 microphone in my hands. And in the end, even with that, there's still a password involved. So of course, we need strong passwords. We need strong passwords so that attackers can't crack them and get into our systems. And in order to have strong passwords, the passwords have to be usable. And by usable, I don't mean easy to remember. That's the easy part of usability. It's actually what usability really means, and the important part is that the user is able to understand how to comply with the requirements and use the system properly and do it with minimal effort. Okay? So, just some background. I'm sure you're all familiar with password rules like these. Some people actually claim that these are standards. I wrote an article about this last year. I actually tried to do the research to find out where these are codified in any standards, like US government standards, and it turns out they're not. Okay, they're actually, the best I could find is they were the default settings in Windows 2000. Seriously, it's actually the first reference I could find to them. So we're familiar with all these, and they're commonly used. Everyone says, well, this must be the right thing to use. But here's the thing. Who actually said that those rules are good enough? Where's the measurement of how strong they make passwords or the proof that they work? Do we have any metrics that show that people using those password rules have fewer password compromises due to password cracking than people that use other sets of rules or people that use no rules at all? And in addition to whether or not they're strong, there's the usability problems, which you might be largely familiar with. The common dogma on password requirements are that we tell people password has to be complex and it has to be different than all the other passwords, which means it's difficult to remember. But then we tell people they have to remember it, right? And then you go into the trouble to remember it, and then we say, well, you got to change it. Okay, so now you got to remember it again. Okay, and if you can't remember it and you do something, and you can't remember it and you type it wrong or get the wrong password, you get penalized for not being able to remember it. So now the user is under pressure to remember it and get it right every time they type it in. And if they have problems with that and do workarounds like writing it down someplace, et cetera, sharing with somebody, whatever, they get in trouble for violating the policy that you gave them that was very difficult. So in the end, I'd say we're actually asking our users to do the impossible, right? It's a pain and it's a total usability failure. It's actually shown by the fact that users often don't follow the rules and do a lot of useless stuff. So we say we want passwords to be strong. What do we mean when we say strong? Well, first of all, we mean we want a big key space. We want a lot of bits in the key used, which discourages brute force attacks. And by brute force attack, this term's really getting misused a lot. A brute force attack is supposed to mean trying every single possible key that can possibly exist in the key space. A lot of people use brute force attack these days when they mean a dictionary attack, which means some subset of those keys that you think might be likely to be used. So you want a big key space, which discourages brute force attacks, and that's all big key space does, is discourage the brute force attacks. And then you want high entropy in the passwords actually used. High entropy is supposed to discourage dictionary attacks by making it infeasible to actually run through a dictionary, right? So that's what we want by strong. And then we also talk about requiring people to change passwords. So we tell people you have to have a strong password, but you have to change it. So what happens with that? Well, password changing costs money, right? It takes the user time and effort. If the user is getting paid for it, that ends up being a cost. There's actually an FAA study that was done several years ago which looked at this. It's a study on usability and passwords and quantified the cost to the organization for password change. And it was exacerbated by the fact that users had different passwords for 20 different systems with different rules on them, with different password aging intervals, so the users were effectively in a constant state of changing passwords for one system or another. It also incurs what usability people call a cognitive load on the user, which is the amount of cognitive effort required to deal with a system. This means the user gets frustrated choosing a new password because they have to come up with something that meets the rules, that's different from the ones they used before, etc. And then they have to memorize it, which takes actually a lot of cognitive effort, especially when you're told don't write it down, you have to memorize it right now, etc. And that makes them use what the usability people call coping strategies, what we often call workarounds. So users do things like you give them a set of rules, so they're going to choose the weakest possible password that meets those rules. So the password rules I just showed you that everyone uses, a password that meets that rule is A, bang, capital A, right? Meets the rules, but a lot of people would think that's not really a thing to do. They often then do a variation of previous. They put a number on the end. They increment the number every time they go through. They write them down even though you told them not to. They stay logged in. They share them with, it's actually documented places people share their passwords with their coworkers in case they forget them. Okay, or they leave themselves logged into systems because they don't want to have to keep typing their password, remember it, etc. So these are all usability failures. Making people change their password costs money. So why do we have password aging? So aging originally addressed small key spaces. So when you had a key space that was small enough that somebody with a lot of money might actually be able to do a brute force attack on it, you need to make people change their passwords fast enough that the attackers couldn't go through the whole key space or go through a small fraction of it. However, it kind of morphed into addressing dictionary attacks by saying, well, if we make people change their passwords fast enough, then even attackers doing a dictionary attack, they'll change their password before the attacker gets it. So that was a nice idea. But in order to do that, you actually have to come up with a lifetime that you think is short enough to thwart an attacker. So what duration is actually effective to thwart those attacks? Here's the problem. We don't actually have any meaningful way of estimating what the value is. All those numbers like 60 days, 90 days, a year, whatever it is, are really all just made up. There's, as Gertrude Stein once said, there's no there. So what you really want, since we know password changing doesn't really help things in terms of usability and so on, the burden on users, the cost of the organization, you want to make it as long as possible. That's right. To discourage brute force attacks, you want to have key space and entropy high enough that the time it takes to do an attack on them gets very big, approaches infinity. But what that really means is infinity just has to be greater than, you have to pick an infinity that's just greater than the lifetime of your system. And if you do that, that means actually users don't have to change their passwords. Basically, if a user has a password that's strong enough, why should they have to change it? If it's not going to get cracked, they shouldn't need to. So it's a win-win for everyone. Right? User doesn't have to change it and you get strong passwords. The rule on writing down passwords or not writing down passwords is a usability problem. But here's the thing, is writing down passwords really a bad thing? Okay, now if you're in the military and you're worried about spies in your organization who are actively trying to get passwords, you know, working at the next cubicle and trying to get passwords, maybe. In a lot of cases, that's really not that much of a threat. Okay, in my organization, I'm not too worried about that. What I'm worried about are remote attacks, people cracking passwords, etc. I think if somebody writes down a password in a safe place, sticks it in a locked drawer or maybe in their wallet or something like that, that's probably good enough. That my risk is really pretty low of somebody stealing that. If I got somebody in my organization doing that, I've probably got much bigger problems because they probably already have passwords to the systems that we care about. And it gets even worse when you tell people they have to remember 100 passwords because they're using Gmail and their system at work and their bank accounts and all these other things. So if we get rid of the writing down thing, it makes it easier for people to deal with stronger passwords, more complicated, harder to remember passwords, which is what we want people to have. And like I said, you want to pick an entropy high enough that it's very hard for these things to be cracked. So to get high entropy, you need the right password rules, which leads to the question, what password rules can you give users for choosing passwords that guarantees that you have enough entropy in your password space all the time? And I think the answer is none. And Warren will talk some about how we looked at this problem and how I came to that conclusion.
Thanks, Abe. So my name is Warren Anderson. I'm a scientist with LIGO, and like many scientists in LIGO, or many scientists in any large scientific project, I end up wearing a number of hats, and one of the hats that I wear is I'm a member of the security committee for the computer security committee. And I think I was put on there mostly to bring the scientific usability perspective to deliberations. But when we started thinking about this question of what password rules guarantee that you're going to have secure passwords, I started thinking about the question of, well, what do users actually do when they choose passwords? And is there some way of looking at how users use passwords that that we can get some insight into where the failure in password rules might come from? So we started working on a paper, Abe, myself, and some colleagues, Rick Farrow and Scott Sakai. And what we did was we looked at 8,500 passwords that were leaked from MySpace. And these are 8-character passwords. They're MySpace passwords, so not probably the highest quality of passwords that one can imagine. But our goal was not to analyze the MySpace password rules as such, but just to use this as a body of information from which we could draw perhaps more general conclusions about what users do when they choose passwords. So the first thing we did was we compared the 8,500 passwords to just a dictionary of English words and the common munges that people use, the elite munges for passwords. Ran them through CrackLib and saw how many of these passwords we could reproduce. And it turned out 21% were susceptible to CrackLib with a 500 million word dictionary. So again, as we said, probably not the highest quality password corpus. Those 21%, I think we just write off as things that we could have checked at the beginning and eliminated. So it's really the other 79% that we're interested in. But it's worth pointing out that, if even with 8 characters, if we had a 500 million word dictionary, we had less than a 1 in 1,400 chance of getting even one of those passwords if they had been generated randomly. So let's suppose that MySpace actually did some password checking with a dictionary before and rejected user passwords. And I'll point out that this could be a very frustrating usability issue, as Abe has pointed out, for passwords in itself, because they type in a password, it's too close to, it's in the dictionary. We say, nope, not a good password, try again. And they put in another password, no, it's in the dictionary, not a good password, try again. We haven't given them any rules about what the passwords they're allowed to choose are. They're just, it can't be in our 500 million word dictionary. Well, how am I going to check that? Only by typing it in over and over again. But suppose that we had done that and just took a look at what's left. So what could we do to try and determine what other things might allow attackers to approach the problem? And the thing that we looked at was, suppose that we look at character patterns. Are there preferred character patterns within passwords, even ones that users are trying to generate randomly, that would give us an edge? So what we did was built dictionaries based on two techniques. One we call the phoneme technique, and basically we just take a look at our cracklib, our 500 million word dictionary, which is English words and common mungings of those, and we look for common character patterns. So 2 and 3 character strings that appear statistically more often in this dictionary that we use than others. Now, some of these words that we're going to find with the phonemes, some of the words in our phoneme dictionary. So some of these words that are going to just come from common phonemes are going to have been in the cracklib dictionary anyways, but some of them are not going to be. They're going to just be different patterns. And I need to go back a little bit. There we are. But we can make all of the 8 character combinations we want out of these 2 and 3 character strings that are common and see what we get. Well, it turns out that if you do the entire thing, the dictionary is too large to be practical. But if you restrict yourself to only lowercase phonemes and phonemes that contain no symbols, so you're actually restricting yourself quite a bit there, even that gives you 2 trillion words in your dictionary that you're going to compare against the MySpace corpus. And what you find, and you'll see that when the projector comes back on, is that 75% of the MySpace passwords are actually in this dictionary that you construct this way. So that means that beyond the 21% that were just English words or common mungings, we have another 50% plus of words that are easily retrievable just by saying, are there patterns that we can look for that people use in their passwords? We also used a second technique, which is similar, and that's based on Markov chains. So in LIGO, we're looking for gravitational waves. We're looking for these little signals in very noisy data. And one of the things that we do in order to try and determine what kind of signal we have if we find one is Markov chain analysis. So it was pretty natural to think about this as a way of doing things too. So what is a Markov chain? A Markov chain is a method of building a sequence. And in our case, our sequence is a string. It's a password string. And the way that one builds a Markov chain is to take, again, a training dictionary, in this case, the 500 million word cracklib dictionary that we used. And for each, given a certain set of starting characters, evaluate the probability for each character to be the next character. And the order of the Markov chain is then how many characters do you look back in trying to determine what the probability of the next character is. So we used a third order Markov chain, which means we look back 2 characters and say, okay, based on these last 2 characters, what's the most probable next character in the string, based on, given our training library. So what we did was did our third order Markov chain analysis. This time, we got a smaller dictionary. Again, we made some, when you do the probabilities, you want to set some threshold on probabilities. We're only going to accept, in our Markov chains, a probability for the next character over some threshold. We set our threshold so that there was 500 billion passwords in this dictionary. So, at least if all the passwords that the MySpace users had chosen were random, we'd have something like 8/1000th% chance of having found a given password, 8-character password. But we found 50% of the passwords in the MySpace corpus. So again, this is a fairly straightforward, reasonable technique for looking for patterns within the passwords that produces a fairly high success rate. Again, 21% were in the dictionary to begin with, probably, but that's over, that's almost 30% that were not found, wouldn't be in this crack-lib dictionary, but that we would be able to find by using a simple technique. So, the message here is that there are hidden patterns in what users do in order to pick passwords. And I don't think that should come as a surprise to anybody. But what was a little bit surprising was just our two first most naive ideas for looking for patterns in the passwords were extraordinarily successful. 30%, 50% of users who didn't appear in the crack-lib dictionary were accessible to finding patterns from the crack-lib dictionary after the fact. So the question then that I want to ask is this just because MySpace has bad password rules? And in thinking about this, my conclusion was the following. Okay, well, we're going to push ahead anyways. So the way I wanted to look at this, or the way I ended up looking at this, was in set theoretic language. So what we're really talking about is sets of things. And from the password rules, we create a set of all possible passwords. And when we think about password entropy, we're usually thinking about the entropy of that set. But that's not the set that an attacker cares about. He doesn't care about all the possible passwords that could be created. What he cares about is what passwords are users likely to choose. And so our policies, our password rules, are actually addressing something that is not what we want to have addressed. What the attacker cares about is the space of user passwords, and what he cares in particular about is that his dictionary, his set, and the dictionary of passwords users are likely to choose, which I'll call the user dictionary, that there's a sufficient intersection of those for a small enough attack dictionary. That's all he really wants. So said another way, password rules don't enforce a high entropy in the user dictionary, the dictionary of user-chosen passwords, because they don't address any of the subconscious patterns that people naturally put into their passwords. And as long as passwords are composed of elements, in this case characters, digits, symbols, which people have previous experience with, that previous experience is going to inform the way that they want to combine those elements into a password. And it's going to do it in subtle ways that we're going to have trouble imposing rules to rule out. So as long as there are correlations within how users choose passwords, then there's going to be some metric on the space of all passwords that one can use in order to bring the attack dictionary to a small enough size to attack just that part of the password space where we have a high probability of getting what we want. The next slide actually doesn't even depend on orientation, so.
So we have the slides up, but you have to say it backwards now.
No, not on this one, because, well, if you could see it, this is just a visual representation. This is a visual representation of a menu from a slide projector. But behind that, there's, yay. So the idea, this is just a conceptual representation where the big blue circle is the space of all the possible passwords that users could have chosen given the rules. But they don't do that. They cluster in these little red dots based on some preconceived notion of how characters are supposed to go together. And so if you can, build the green ellipse that contains a lot of the high value dots and doesn't have to attack the whole space, you're in as an attacker. So the take-home message is that people are bad at random. And that's not news, actually. Psychologists have actually studied this. And what they found is that when humans try to be random number generators or random generators, they're actually well modeled as hidden Markov processes. So surprise, surprise, turns out that Markov modeling actually does fairly well at predicting what people will do. Now, people have often, I've often heard from my physicist colleagues, well, yes, but I heard passphrases should solve this problem with passwords. Well, it solves one problem. It solves, I can remember something that comes from a space with a lot more entropy more easily. But as we already discussed, it's not the entropy of the space you're choosing from that's the problem. It's how are you choosing? What's the entropy that you're imposing by your choices? And again, passphrases are associated with natural language. We have some preconceived ideas about how words go together. Unless you're saying doing good, adjectives shouldn't follow verbs, right? Should be doing well. But in general, we know that adjectives don't follow verbs. Adverbs follow verbs. So when I make my passphrase, pulling it out of my head, what am I going to do? I'm probably going to have an adverb preferred over an adjective following my verb. So the same problem exists. There are preconceptions, there are patterns that we're going to impose based on the fact that we already know how language works. And I don't think passphrases solve the problem. So at least based on the work that we've done and what I've been able to take away from it, I don't think there are rules that can force people to choose randomly. And choosing randomly is the only way that we fill out that space of all possible passwords and really get the entropy that we think we're getting. So with that, that's the analysis that I did and fed back into the security policy. And Abe, our security officer, is going to tell you what the result of that analysis, that feedback is.
I'll also actually add a comment on what Warren was talking about. The really nifty thing about doing Markov chain analysis on this stuff is that you can take actually any set of passwords and do the analysis and use it to predict other passwords. So you can take any set of password rules, take a bunch of passwords that users have chosen under those rules, and use those to model other passwords that users might pick. So the simple example is you tell everyone will put a digit in their password. Most people put a digit at the end of the password, so you can build a model that says we'll generate a dictionary of passwords with digits at the end of the word, etc. So that's one of the reasons also that user password selection fails, is because an attacker can adapt their dictionary building to the rules that are being applied in any particular environment. So we took a look at this. We actually kind of started down this road because I said, I want to come up with a password policy that actually works for us, that is actually effective. If I'm going to impose rules on our users, I want them to be able to, I want those users to be worthwhile. I don't want to make them do a bunch of work for nothing, because it's just going to annoy them, and then they're not going to listen to me the next time I ask them to do something that's annoying. So I Unlike a lot of security people, I actually try not to annoy my users. So we were trying to come up with another set of rules. We went down the road of this analysis, kind of came to this conclusion that the rules don't work. So we came up with what in some ways is the obvious solution, but is amazingly really considered anathema by a lot of people. So our solution is users are not going to really get to choose passwords. They don't get to choose their own passwords. We're going to generate passwords using a random source, and we're going to give the user a set of options. You can choose one of the following candidates, and that's your password. So we give the user a little bit of choice, so they get a few options, and I'll demonstrate our examples in a moment. Then we tell them, so that's the kind of the stick, right? The carrot is we tell the users, you're going to get this one password. You're going to have to select from the set. You don't get to choose your own, but I'm never going to make you change it unless I think it's compromised, or we determine the hashing algorithm's compromised and we need to reset everyone's password, etc. But you've got a strong password. You can keep it for as long as you can. Hopefully, ultimately, the lifetime of the system. Tell users it's okay to write it down. Yeah, I know it's a little hard to. It may be a little hard to remember. Although I'm going to demonstrate in a moment, I think you can do random password generation that actually is relatively easy to remember. Notice I said relatively easy. But it's okay to write it down. Just put it in a safe place. Don't leave it stuck on your monitor, and that's okay. And the other thing goes with this is we have a single sign-on system. So I'm also telling users, you've just got one password you have to deal with. You're not going to have a different password for each system, and we're going to minimize the amount of times you have to enter it. Now, we don't have fully single sign-on. It's single sign-on and common sign-on. But it's still one password to rule them all. So the trick to doing this, I find, is to give people a variety of password choices in a variety of ways. So so a lot of people, when I say random password, they think the bottom example is line noise. Random just means they were generated using a random source. You can have a random passphrase. So we built a dictionary using something around the 10,000 most common words in the English language, and then we just randomly choose from them. We use the combination of the dictionary size and the number of words to get as much entropy as we want. So the passwords have to have n number of words and be a total of at least n number of characters. You get short words, you get more words in it. But here's a couple examples of passphrase. Some people may not want to type that much and may want a shorter password, so they can choose for something shorter. We give an all alpha option for those people using iPhones and iPads, where entering anything but lowercase alpha is a real pain in the butt. But some people may prefer to type even less, so they can get alphanumeric or mixed case. Or if they really want the shortest possible password, we give them something with a full character set. All of these examples have basically about the same amount of entropy in the password system, or the same minimum entropy given. So they're all equally strong as far as we're concerned. And we let the user, we give the user a couple of choices. We let them press a button and get another set of choices if they're really unhappy with these. Our experience that we found so far that you go through 2 or 3 passes at this and you find a passphrase that you're comfortable with. And I have found myself, I'm using these, so I'm also using these, say, for things like root passwords in some places. So I actually have a handful of these. And just experientially, I found that about 5 times of entering, so I like the passphrases, most people do, about 5 times of entering these things, and I've actually got it memorized. And for those of you that are familiar with the XKCD Correct Battery Horse Staple cartoon, they actually kind of stole our thunder. We were working on this when that cartoon came out. But he's basically right, and it actually does work, and it seems to work pretty well. The other experiential thing I found is that people tend to react negatively when I say, you're going to get a random password. But when I show them the passphrases on top, they say, well, that's not so bad. And then when I say, and you'll never have to change your password, they say, I really like that. So, which also lend some credence to my notion of the cognitive load of dealing with having to do password changing. It turns out that is way worse on people than having to have a random password shoved down their throat. And with that, I think it's time for questions. Please, there's a microphone. He got to it first.
Hi, I'm Dan Klein.
That looks like Dan Klein.
Spent a lot of time thinking about this thing. I did some research back 25 years ago, which I know you know about.
We're actually referencing you in our paper.
I'm sure. Anyway, I agree these are strong passwords. I disagree that they're usable, but okay, fine, you can write them down. But I also disagree with your assertion about Markov chains. Markov chains are based on knowing something so that you can find something, and if you don't know where it starts, it's kind of hard to apply that to cracking a password.
So these Markov chains were based on the cracklib dictionary. So it was just English words and common mungings. And were already remarkably successful. So we didn't have any advanced knowledge about what we were looking for. It was just English words and leet substitutions.
Right, and therein is half of the problem because the alphabet isn't big enough. If you don't use leet substitutions, if you use intelligent substitutions, you increase the size of your directory. If you use symbological substitutions, then you increase the size of your character set until you wind up with an unsearchable data space. So I've got a 21 character password and you're not going to get it because I do intelligent passphrase substitution. I think the rule that you really want is don't be stupid. And stupid is defined much more broadly than most people would think. You need to educate them what the smart choices are.
So, yeah.
And that's never going to happen.
Right.
You know, welcome to my fairy tale.
Yeah, I understand. Yeah, I understand your point. But I think the problem is exactly enforcing those rules. The "don't be stupid" rule on users, right? I mean, it's certainly true that one can, given a set of given rules, choose a password that is arbitrarily strong because given the rules, I can put those rules into a random generator and get out a random password that doesn't have any of my preconceived knowledge in it. The problem is getting every user to do that. And
another argument is don't use words longer than a certain length and have it be of a certain length and create a passphrase that's intelligent. If I can scan it with an algorithm, knowing what the plain text is, then it's not good enough. And proactive checking is always better than trying to crack things and figure out if they're guessable. But anyway, yeah, thank you.
Let me just make a quick comment on proactive password checking. It was a great idea at the time. When I was at SDSC, we used it. It worked really good. But here's the thing. We originally tried that approach, but these days there are much bigger dictionaries you can build. And I went and used Google Ngrams to build the biggest, fattest dictionary I could build, which I think we ended up with substitutions and other things, we ended up with something on the order of 4 billion words, something like that. So we actually did that, and we built a password changer that checked against all those words. It was a usability disaster because nobody could figure out what passwords were acceptable and what weren't. And they got really frustrated trying to come up with a password that would pass. They kept trying to say, no, you can't use that one. No, you can't use that one. Yes, you can use that one, even though it didn't look that different from the other one that they'd used, to the point where people are starting to just bang on the keyboard. And actually, it's a great way to force users to generate random passwords in the end. But it basically, as there are better dictionaries available, it doesn't scale well.
I just wanted to add one more thing, which is if you remove enough choice from the user that they've had to try 100 things until they can't even recognize how they came up with their password anymore, are we really doing a disservice to them by just giving them a random one to begin with? It won't have any less meaning to them than the one that they eventually settled on after that many tries.
Hi, you let users kind of cycle through till they find a password that they like.
I'm sorry.
You let users cycle through these till they find a password that they like. Have you gone back to analyze the passwords they choose to find out if they're clustered in a way that makes them easier, reducing your entropy?
No, we haven't. We actually don't have enough data, but
But yes, it will. So the
Yes.
question is, will it reduce it as much as just letting them have free choice? And I strongly suspect the answer is no. If we even limited it after 10, there will be patterns emerging, but I suspect they'll be much weaker than the ones that we find when you just let people choose on their own.
Yeah, me too.
So,
it better not be a pun.
No, hacker here. So shoulder surfing any of these passwords would not be difficult because people are going to type them really slow.
We're not addressing password theft at all.
Well, to that point, so one of the things I do is I always test how fast I can type a password once I've chosen it. I think these passwords are good. Everybody agrees passwords suck. There's not a lot of good answer here. But the unfortunate side of it is I think there's also, I've been playing around with 1Password and LastPass and some of the other ones to see about what they generate. Say, give me a conveniently cryptic 16-character password. And most of those are pretty good. The entropy is not too bad on them. But the key, one of the things I honestly do think about a lot is how fast can I type them and how easy is it for me to pull the information from. Have you guys looked at that aspect at all, or are you just making the assumption that if you make a really cryptic password that's really hard to type, you're willing to suffer the possibility of shoulder surfing and the increased support calls because people are going to mistype it 3 times and get locked out, and now they got to go change it again?
Yeah, so on the first part, yeah, like I said, I just don't, for us, I consider that not much. It's a risk I'm willing to accept. In some environments, it may not be, and you have to think about that. When I pick from these, I look for ones I think are relatively easy to type. I might also argue that actually typing, if you're an English speaker, typing English words, it's probably easier to type them faster if you're a decent typist than random characters. I haven't proven that, but I intuitively I think that's the case. The support call issue, well, basically it kind of boils down to the same things, the ability to type. But then there's also support call issues if people can't remember their passwords, et cetera, so on. Hasn't seemed to have been a big problem.
Hi, Börje Sandung, Chalmers University. I would just like to add a comment.
Can you lean into the microphone a little bit?
This is the last one, please.
Börje Sandung from Chalmers in Sweden. I just like to add a comment on the password. We generate passwords for the users when they come to us, and they look like the full chart set you have. And it's amazing that almost everyone keeps that password. They learn it really quick and keep the password. They don't, they get it on a chart when they got to us, but they learn it and they type it really fast. So it's possible to do it, and they can also. If the password seems to be hard to write, get another password. But they are allowed to choose passwords, any kind of password they want, according to some rules. But they normally don't do it. They accept the password.
That's actually really interesting to know. It's just interesting because lots of people I have this conversation with says, our users will not accept it if we just give them passwords, that sort of thing. It's actually, psychologically, it's very interesting, but that's interesting to hear that.